Water is an amphoteric substance, and that's the same as our sodium hydrogen carbonate or baking soda. It can act as either an acid or base. And so there's a really important equation that's the ionization of water. So if you have water plus water to a very small degree, so I'll write a little arrow, mostly it stays where it is. One of the hydrogens from this water can go join these hydrogens, so we'll end up with the hydroxide ion, and that's aqueous, that doesn't look very good, plus the hydronium ion, H3O plus, also aqueous. And that happens only to a small extent, because if you look at the reaction, you tell me I'm crazy. You put water in water, what happens? Nothing. But it ionizes just very slightly. But that slight amount is really important. Another way to look at it is just thinking of a water molecule breaking into the ions. Only a little bit does this happen. It forms H plus and OH minus. And I wrote them in the other order. The order you write your products in doesn't matter. They're both there. Okay, so water breaks apart just to a very small degree. How small? Pure water. The two concentrations will be equal. So water always contains both of these ions. And the square bracket, you see right here, the square bracket means molar concentration. So I read that. The molar concentration of H plus is equal to the molar concentration of OH minus, and they're equal to 1 times 10 to the minus 7 molar. That's a very small number. So it's a very small amount that water ionizes. And it turns out that any water solution, if you multiply those two concentrations together, so 10 to the minus 7th times 10 to the minus 7th gives you 1.0 times 10 to the minus 14th. And that's true whether they're equal to each other or not. And this is an important number known as the KW, or the equilibrium constant of water. And what that means is if you increase the H plus, so it goes up, the OH minus will go down, and vice versa, but you always have both of those in a water solution. Let's look at how we can use this equation in a calculation. Here's a problem. Calculate the molar concentration of hydroxide ion in a solution where the hydronium ion is 7.5 times 10 to the minus 5th molar, and then determine if the solution is acidic, basic, or neutral. So the equation we're going to use is that the OH minus times the H3O plus, or you can call it the H plus, is always equal to 1.0 times 10 to the minus 14. And it actually doesn't have units. We'll use molarity, but we don't use the units in our calculation. So it's algebra. We plug in what we know and solve for what we don't know. Okay, let's think about our given and our find. Given, we have 7.5 times 10 to the minus 5th molar of the H plus, and our find is the OH minus. Okay, so we'll put this number right in here for our H3O, and we'll find the OH. So OH minus times 7.5 times 10 to the minus 5th equals 1.0 times 10 to the minus 14th. And to solve for OH, we're going to divide both sides by 7.5 times 10 to the minus 5th. Divide by 7.5 times 10 to the minus 5th. And now I'm going to do that on my calculator. So I get out my calculator, and remember to use the exponent key. So 1 exponent 14 negative divided by 7.5 exponent 5 negative equals, and I get 1.3 times 10 to the minus 10. And that is going to be molar, and that's my hydroxide ion concentration. So I solved for the OH. My next question, is it acidic or is it basic? And I compare these two concentrations. So my H was 7.5 times 10 to the minus 5th. My OH is 10 to the minus 10. Well, which one of those is bigger? 10 to the minus 5th. And so since the H plus is bigger, this is acidic. Oh, here it is written out, but we can't even see it over my messiness there. You can check the other slide on the PowerPoint to see that more clearly. So here's the solutions to the last slide. More clean. It turned out quite a mess on that last one, but now you can read it. The pH scale is another way to represent the concentration of H+. And the reason we use the pH scale is very often in water solutions, our concentration of H+ is a small number, like our previous example where it has a negative exponent. So the log comes in handy. So our equation for log is that the pH is equal to the negative log of the concentration of H+. And nobody likes that because everybody's scared of log. But the log is the exponent. Okay, so the pH is the exponent. But the negative is here because we don't want to keep saying it's negative. So the log is the exponent. Acidic solutions have pH less than 7. Basic solutions have pH greater than 7. So let's look at an example. If the concentration of H3O plus is 1.0 times 10 to the minus 3, okay, the pH is 3. It's the exponent. If your H plus is 10 to the minus 7th, the pH is 7. The pH is the exponent. So that's the neutral one. Remember, that concentration is neutral. So pH 7 is neutral. The one above it, the pH 3, that's acidic because it's less than 7. And then if the H plus is 10 to the minus 10, 10 is the pH. And that one's basic because it's greater than 7. This is a simple case when you have a 1 here. So as long as it's starting with a 1, you can just take the exponent, and that is the pH. If it's not a 1, for example, this problem right here, 2.1 times 10 to the minus 3, that's not a 1. So our pH, you might think it's about 3, and it is about 3. It's 2.68. So you just plug it into the equation with the log in it on your calculator. I'm actually not going to ask you those on the test, but they're easy to do if you have a calculator with a log button, so I recommend that you try it. And the pH scale is really handy for a lot of natural solutions fall in the range of pH from 0, which is very acidic, to 14, which is very basic. So right in the middle you have distilled water, and that's neutral. And on the acidic side, you see we have some compounds here. Gastric acid, that's in your stomach, very acidic, near the lowest end. And then we have on the basic side some also solutions. You see the baking soda there, and bleach being a very basic solution. Let's look at some practice problems and see what we can calculate. So we want to calculate the pH of the following solutions. Also find the hydroxide and tell if it's acidic or basic. So the first one is vinegar, where H plus is 0.001 molar. What I want to do with that is change that to scientific notation, because if I want the exponent, I got to get it in scientific notation. So reviewing that, I'm going to move the decimal to here. So I'm going to call it 1 times 10 to the minus 3 molar. And now that's in that form, we can see that the pH equals the exponent, which is 3. So now we can tell if it's acidic or basic. pH 3, that's acidic. The other question it asks is to find the hydroxide. And now we're going to go back to that equation that the H plus times the OH minus is equal to 1 times 10 to the minus 14. Now the previous problem we put in numbers and calculated it. But if you remember from the rule of exponents, that when you multiply the numbers, the exponents add. So we can use that simple rule if this one was a minus 3 exponent. In order to add to minus 14, this one has to be minus 11. So our concentration of OH minus is equal to 1 times 10 to the minus 11, because, we get a different color here, minus 3 plus minus 11 equals minus 14, which is that exponent. So it just simplifies it. You can do it the way we did the last one and put it in your calculator as well. They both work. So pause the video, try some of these, and then turn it back on. So antacid has an H concentration of 10 to the minus 9. So what's our pH? It's the exponent, 9. So 9, that's greater than 7. This is basic. Oh, that's an S. Sorry about that. Let me erase that. It's basic. Then to calculate the OH minus, the 9 plus some number is going to give us minus 14, and that number is minus 5. So 1 times 10 to the minus 5 molar, and this should be molar as well, is our concentration of base. Find the H plus and the pH when the OH minus is 10 to the minus 9. Now be careful, because you don't want to take this exponent, because that's the OH. Remember, the pH comes from the H. So the first thing we want to do is calculate what the H is. So the first thing we're going to do, and I'll erase all this, we're going to use that number. We're going to, if the OH is minus 9, what does the H have to be to add to minus 14? So our H has to be 1.0 times 10 to the minus 5. Because minus 5 minus 9. And now we can find the pH from this one equals 5. So be careful. If you're given the OH, first find the H, and then you find the pH. So would this be acidic or basic? pH of 5, that's acidic. We can also go the reverse. If we know the pH, we can find the H and the OH. So let's look at lemon juice. Has a pH of 2. So from that, we can find from the pH gives us the H. So we know our H plus is equal to 1.0 times 10 to the minus 2. Remember, because the pH equals the exponent. So we know our H. We can also find our OH, because here, let me go with a different color, the 2 plus whatever number is on the H is going to add to the minus 14. So 1 times 10 to the minus 12, because there, minus 2 plus minus 12 equals minus 14. And would that be acidic or basic? Well, pH of 2, that's acidic. What if we had a pH of 5? We also know right off that's acidic, less than 7. Okay, and if the pH is 5, then we know the H is 1.0 times 10 to the minus 5. And then the OH, the 5 plus something is minus 14, so that's got to be 1.0 times 10 to the minus 9, because minus 9 plus minus 5 gives us minus 14. And the last one, ammonia, has a pH of 12. Well, that's basic, because that's bigger than 7. And we know our H plus is going to be 1 times 10 to the negative 12, because remember the pH gives us the exponent on the H, and our OH minus has got to be whatever minus 12 plus something equals minus 14, so this is 1 times 10 to the minus 2, because those two add to 14, and these are molar. So these are some examples that are similar to what I'm going to give you on the test. They're the simple ones that have the 1 in front of it with whole number pHs, but it's more important to me that you understand the concept of pH rather than know all the details of the calculator. And here it is written out more clean. Let's look at buffers. A buffer is a solution that will resist the change in pH. It contains both a weak acid and that weak acid's conjugate base. So in the example I'm looking at right here, the weak acid is this, acetic acid. And its conjugate base, remember, to get the conjugate base, you take off the H. So the weak base is right here, and that's the acetate ion. So the acetic acid is your weak acid. It's a weak acid. And this is the conjugate base. A buffer solution will contain both of those in about equal amounts. So it has both of them. Buffers are really important. Human blood is a buffer. The pH of your blood and most body systems is very sensitive. So if your pH goes up or down much, your body can't function. So systems that need to have a constant pH often have a buffer. And what happens with a buffer is that the conjugate base will react with any acid. So if any acid is added to this system for whatever reason, H plus, what will happen to it, rather than changing the pH, it'll react with this conjugate base to give you more of the weak acid. So you already had that weak acid. It's not affecting the solution much. And if any base is added, that hydroxide will react with the acid portion to give you water and the conjugate base. So you can see adding acid or base doesn't change the pH. What it does is changes the balance of how much of the weak acid and how much of the conjugate base you have. Let's look at this example. Which of the following is a buffer solution? And apply this concept that we've got to find a weak acid and its conjugate base. If it doesn't have both, it's not a buffer. So let's look at the first one. We have H2SO4 and H2SO3. Do we have a weak acid? Yes, this is a weak acid. So we do have a weak acid. Is H2SO4 its conjugate base? No, it's a strong acid. So we have a weak acid and a strong acid. That is not a buffer, so not this choice. How about HF and NaF? Do we have a weak acid? This one right here is a weak acid, hydrofluoric acid. Is NaF the conjugate base? Well, remember the conjugate base? You take off the H, and what's left? It's the F. Well, then we just put a spectator on it. So that's good. That's the conjugate base. So that one is a buffer right there. Let's look at the others and see if we have another buffer here. HCl, is that a weak acid? No, that's a strong acid. So strong acid. How about NaCl? That's neither. That's a salt. So not the conjugate base. We actually have a strong acid and its conjugate base. I'm going to rewrite this because it's looking a little messy. Okay, so not a buffer. And then NaCl, again, we have a salt. And NaOH, we have a strong base. That's not a buffer. A buffer could be a weak base and its conjugate acid as well, but it's not going to be a strong base. So our answer is HF and NaF. Titration is a method of finding the concentration of an acid solution using a solution of a base with the known concentration, or vice versa. Here's what the apparatus looks like. So this is a burette, and in the burette we have the base, sodium hydroxide. And this burette is an instrument that carefully will add the base and measure how much is added. And you can see the markings on the side showing that. In the flask we have the acid. In this case, it's acetic acid, HC2H3O2. And we have a measured volume of it, but we don't know its concentration. So we know the volume of the acid, and we know the volume and the concentration of the base, and from that we can find the concentration of the acid. So let me show you how the calculations work. Consider a titration of acetic acid with sodium hydroxide. 10 milliliter sample of acetic acid. So we know we have 10.0 milliliters of acetic acid requires 37.55 milliliters of sodium hydroxide, and its concentration is 0.223 molar. And remember, molar means moles per liter. And what we're trying to find is the molarity, or the moles per liter, of the acetic acid. So we know the volume. So this is going to be moles per liter. We know the liters. This number right here, we're going to use for the liters. And then these two pieces here, we're going to use to find the moles. So the way we do it, we start with our number that has 1 unit. We'll start with 37.55 milliliters of NaOH. Now really what I need is liters. So I'm going to change that to liters by the conversion that there's 1,000 milliliters per liter, and cancel the milliliters. Then I'm going to use the conversion that we have 0.223 moles of NaOH per liter of NaOH. Okay, so notice this is stoichiometry. I'm taking the volume times the molarity to get moles. And now what I need to do, I have the moles of NaOH. What I need is the moles of acid. And in this particular reaction, it's a 1-to-1 ratio. So if I had a different mole ratio, I'd need that. But in this case, I'm going to put 1 mole NaOH on the bottom per 1 mole of HC2H3O2 on the top. Okay, and then the moles of NaOH cancel, and that gives me moles of acid. So now I'm going to my calculator. 37.55 divided by 1,000 times 0.223 equals, and I get 0.00837, and that's keeping 3 significant figures, and that's what I have here, 3 sig figs, so I'm going to stick with 3 moles of HC2H3O2. Now what I wanted was molarity. So I'm going to take those moles and divide it by the volume. Well, I have the volume in milliliters, 10.0 milliliters, and I need to change that to liters, so 1,000 milliliters per liter, or I could just move the decimal, and that would work too. So divided by 10 times 1,000, and I get that the molarity equals 0.837 moles per liter of HC2H3O2. And that's the answer right there. And here it is typed up so you can read it a little bit better. And the essential skills: identify strong, weak, and non-electrolytes, recognize acids and bases, complete and balanced neutralization reactions, recognize common strong and weak acids and bases and know why they are different, understand association of water and find the concentration of hydroxide ion and hydronium ion from the other, simple pH calculations, recognize buffer solutions and why they work, and titration calculations.